Hi, Adriana. I am going to go over a couple of the things for molecular geometry and then Vesper theory just to kind of like get us back to square one. So that's what I'm going to go over in this video. So if that's not what you needed help with, then just ignore this, I guess. But I'm going to take you through kind of just like how to draw them out and then how to identify using the chart like which one they are. Once you get these down, they're really not too bad. They're not too hard, but it's just a matter of doing it and then I like being able to identify them on the chart. So I'm gonna turn my face off here and we're gonna get started on this. Unfortunately, the bell is probably gonna ring here in about 2 minutes, but we can just ignore that. So let's look. We were talking about ionic bonds and covalent bonds prior to this. So we know that in ionic compounds, you are transferring electrons from one atom to the next. Okay, so that's what this example is here. So this sodium has only one on its valence shell, so it's going to transfer that over to chlorine. So it's going to completely lose that outer shell, right? And then chlorine's going to gain that electron. So that's what our ionic bonds are. And then when we're looking at covalent molecules, we're sharing. Okay, so these electrons are being shared by both parties. And there's a way that we can show that. So if you're looking at this, and I'll make this screen bigger here in a second whenever I'm done bopping around. But when you're looking at these, I'll just make it big now. Specifically the oxygen, right? So we've drawn the covalent bond between these two oxygens, and you know that this oxygen has 6 valence shell electrons, and then the one on the left also has 6. So they both need 2 more valence shell electrons to satisfy their octet rule. So, or to fill up their shells. So we're going to draw these circles, right? This is fine for just showing a covalent bond, but in the future, like when we're starting to draw our bonds for Vesper theory, it's going to be more useful to draw them with the dashes in between to represent the bond. So kind of to break this down, this is what we started out drawing. Okay, and then if you had, there's one or two teachers I think there's one teacher at the ninth grade center that shows it like this. So either way, either of those is correct. But here you can see that they're just showing they're circling the two that are actually sharing. So that's what this is saying, is that both of these oxygens are using both of these electrons. So same for this. This is further simplified here by this one. So you have 2 oxygens and then you have a double dash, which represents a double bond. So what these dashes represent is 1 electron over here and 1 electron over here. The dashes are like in place of the circles with the dots. Okay, so you're just inserting these instead. So that's how we're going to draw these out for our Lewis structures. Okay, so another set of examples here, like with hydrogen, they each need 2 total to fill up their shell because hydrogen is very small. Anything other than hydrogen and helium is going to need 8, but hydrogen is small, it only needs 2, so it's going to have a single bond here. They're sharing these electrons for each atom, so you would represent it like this. Oxygen, we just talked about. Nitrogen is going to be a triple bond. Triple and quadruple bonds really don't happen very often, but you could see that here with the nitrogen. So each of these have 5 to begin with. They need 3 more, so they're going to share 3 pairs of electrons, which is represented with this triple bond here. So what we get with all this when we're writing out our Lewis structures, not everything on the central atom will bond, and that's okay. It doesn't have to with a covalent bond. It's not going to bond every single thing on it. So what you end up with are these lone pairs. These are sets of electrons that are not bonded to anything. So if I drew this out, this would be H2O. Okay, so I know I would have an H here with 1 dot. Let's see if I can't just draw this here. Let me get myself a little pen. Okay. All right. So if I drew this out, I'd have H with its 1 dot. I'd have O with its 6 dots. And then I'd have another H on this side with its 1 dot. So if I wanted to go back in here and draw my circles for all this, I could. I could say that H needs one more, and we're going to circle it like that. And then this hydrogen also needs one more. We're going to circle it like that. I could then come in and say, okay, oxygen has 6. It needs 2 more, so it's going to share these. And that's fine. You could do that, but you can kind of see how comparing the two of these, this one that's typed out, it's much easier to identify where the lone pairs are rather than this one. You'd have to do some digging to realize, like, okay, these aren't circled anywhere in either of these. So for this section of things, I would recommend drawing out your Lewis structures like this. So let me turn off that. Let me get back to my marker. Let's see. Oh, I'm going to erase that. All right. So with VSEPR theory, what that is these little molecules across the bottom here, if you're looking at those, that's representing your Lewis dot structure just as a what they call a ball and stick model. So what the balls are representing the atoms and the sticks are representing the bonds between them. So you get different shapes kind of depending on where those electrons end up. So if you think about it this way, like each one of these, this little menu at the bottom is going to pop up. So if I looked at like this, each one of these is representing like an atom, right? So if this is BRF3, the center one is going to be the bromine, and then you have 3 fluorines around the outside. So they have energy of their own, right? So this fluorine has its own electrons. It has its own little like electron cloud, and they want to be as far away from each other as they possibly can be. Electrons, if you want to think of them this way, they're antisocial. Okay, so they don't want to be next to another set of electrons unless they have to. So with these, if you look across the bottom, I don't want to move the mouse again because that little menu will pop up. You won't be able to see it. But if you start on the left-hand side where the carbon dioxide is, you can see that you have the carbon in the middle, which is the black ball, and then you have 2 red ones on either side, which are your oxygens. These are double bonded, which would make sense because if you drew out your Lewis structure, you would have some double bonds there. So I'm going to draw this out just like up here. So if I have carbon and I have oxygen and I have another oxygen, these are going to end up, let's get all these in here. Okay, so each oxygen has 6 valence shell electrons, and then carbon has 4 valence shell electrons. So if I was going to come in here and start drawing circles, I know that this pair has to share, and so does this pair. Okay, so that's a double bond. So all we did was replace that down there. And then this is going to share, and this is going to share because that gives 2 to this oxygen, 2 to that oxygen, and then 4 extras to carbon. So if I was going to draw out the Lewis structure for this, I would write it like this. Okay, somebody just popped in here, so sorry for the awkward pause. So I'm just going to restart what I was talking about. So with the carbon and the 2 oxygens, we have a double bond here and then a double bond on this side. So if I was going to write this out as a Lewis structure, I would write this out like this. So these are supposed to be straight. It's a little bit difficult for me to write on this pad. So you'd have your remaining 4. Okay, and then everything on carbon is bonded because these dashes are in place of the dots that were there. Okay, so on carbon, we had 4 dots on it, right? We know that it's bonding. So this dash is representing 1 electron for carbon and 1 electron for oxygen. So same thing for here. So these oxygens have some pairs left over. We're not paying attention to lone pairs on the outer atoms, only the central atom. So if you looked at this, there's no extra electrons on this carbon. So you would say that there's 0 lone pairs. Okay, so if you had something like this with SO2, you can see that the shape is bent. And back to the shape again with this carbon dioxide, because there's no lone pairs, these oxygens are able to get as far away from each other as they possibly can, which is what they want to do. They're completely repelling each other. That's what that's what VSEPR theory is. It's the valence shell electron pair repulsion theory. So repulsion being the key word there. So since there's nothing else on this carbon adding any more like electron fields to be repelled from, these two are just going to be a straight line because they're going to be as far away from each other as they possibly can. So if I measured that angle from one to the other, you would get 180 degrees. Okay, so that's just something that will be on the chart when you read it, and you'll be able to identify the shape of the bond by how many ways it's bonded and if there's any lone pairs, and then it will tell you the name of the shape and the bond angle. So if I look down here and I have SO2, you can see that it's bent, and I'm going to show you why. So if I start drawing this out, and I have S in the middle, and then I have O on either side, I would look on my periodic table and see that sulfur has 6 valence electrons. So it has 1, 2, 3, 4, 5, 6. And then oxygen has 6. Okay, so I'm just going in and I'm going to kind of draw over some of these dots. All right, so we know that there's 6 here. If this oxygen has 6, it needs 2 more. So I'm going to replace those lines with a dash and say that it's double bonded on this side. Same thing on this side. I'm going to replace those dots with a dash and get a double bond. But what you notice, it's similar to this, right? But what we have here is on the top, we have this lone pair. And what that does is it gives you this like large area of repulsion. Okay, so that's why this is bent. That's why this shape gets kind of like squished over, because you have this area up here that's also repelling the 2 oxygens away from it. So instead of being able to be linear like this, it's going to have a bent shape because these lone pairs that are left over. So that's what's happening with all of these shapes. So like the NH3, the trigonal pyramidal, there's an unspoken pair right here. So if I were to put that on there, I could say that there's a dot there, then you have like this big area of repulsion up here because there's 2 left over, because it's nitrogen has 5, 3 of them are bonded with these hydrogens, and there's 2 left. So you have this area of repulsion at the top, which is pushing these down and away from it. Okay, so they're as far away from each other as they can be going around the central atom, because there's 3 of them. It kind of makes a triangle, but then they're also pushed downward because of this electron area up here. So same thing with this, like trigonal planar. Pyramidal means that it's kind of bent like a pyramid. Planar means that it's just flat. So this one would be flat. There's no lone pairs left over. T-shaped, it gets, has its own shape because of pairs left over or not. So that's basically what these are. So let me turn this off. Actually, let's erase all of this stuff. Okay, so let's go through a couple more examples. This is one way to look at it. This is not my favorite chart. My favorite chart doesn't fit nicely on a slide. So actually, let's go back and look at a couple of these. All right, so here's just some more examples of that. So if I had something else like this, so H2O, there's going to be a bond here and a bond here. That's going to use up 1 electron on each side for this oxygen. So oxygen's going to end up with 2 lone pairs left over. And that's going to make it bent, because you can imagine that there's this huge area of electronegativity up the top that's repelling the other atoms away from it. Okay, so something like this. The Lewis structure is here kind of on the left, and it shows you that this carbon has bonded, it's double bonded to the oxygen and single bonded to all the hydrogens. And because of that, you're going to have them is spread out as far apart as they can be from each other. So there's no lone pairs. This carbon has nothing left over to give. It has started with 4, and it has bonded all 4 of them. So there's no extra lone pairs. There's 3 bond angles or electron angles, and no lone pairs. So you can identify it on the chart using that information. So this one, very similar to the last one, okay? Like look at this and then look at this one. The only difference is that there's a lone pair at the top. So what that meant was that this nitrogen started with 5, so it had 1, 2, 3, 4, 5. It bonded once to each hydrogen, which used up 3 of them, but then it had this 1 left over. So because of this 1 pair up here that's left over, it's going to create this big like area of electron repulsion, and it's going to push these 3 down away from it. So that's exactly what's going on with all of these. So first we just have to like master getting the Lewis structures drawn, and then we can identify them using one of these charts. So let me pull up the chart that I really like. Let me put this on the tab that we are talking about. Okay, so this, hi, there's my face again. This chart's the one that I really like because I feel like it's easy to read. Okay, so let's start on this side where this boron and chlorines are. So if I drew this out and I have my Lewis structure drawn, we know that boron would have started with 3 electrons in its valence shell. So it has bonded to each of these chlorines. Everything is happy. There's nothing left over. So what we have here is we have 3 electron groups. So the groups include lone pairs and bonded pairs. Okay, so that's the first thing you want to look at. Like I have 1 electron group for each of the atoms that's bonded on there. And then if there is a lone pair, that's considered an electron group. So for this one, there are 3 electron groups coming off of the central atom. There are 3 bonded groups because it's actually bonded 3 different ways. And then there's no lone pairs. So that's how you would identify that using these numbers. So electron groups, there's 3 total. 3 of those are bonding groups. There's no lone pairs. So for the actual name, you want to go for the molecular geometry. The electron geometry is kind of like an umbrella term, but we want the specific names for it. We don't want the category it's in. We want the actual name of its geometry. So you can just skip this column. So here with the molecular geometry, you'd say that the shape of this atom or this molecule is going to be trigonal planar, and it's going to have bond angles at 120 degrees. Okay, so this would be the Lewis structure, and then this is a ball and stick model. So those are 2 different things, kind of depending on what's being asked of you. So here with the Lewis structure, it shows all the bonds and then if anything's left over. And the ball and stick model just gives you a representation of the shape. So trigonal planar means that this is a flat molecule. Like if I laid this down on the table, it would be flat. It wouldn't be bent upward at all. And then it has an equal distance between all of the bonds. Okay, so if I go down here and do I don't know, let's do a harder one. So this one, okay, here where we have the chlorine and the 3 fluorines. So chlorine we know has 7 valence shell electrons. So we would have put in the 1, 2, 3, 4, 5, 6, 7. Each fluorine also has 7. So they are going to need to bond once. So a single bond to the central atom to fill them up. So once we do that, this fluorine, like this bond, remember these dashes are in place of dots, okay? So there was a dot here for fluorine and there was a dot here for chlorine. Now this dash is there in place of that just to represent that those electrons are still there, but they're sharing now. So here we've done that for each of them. So all these fluorines are satisfied. There's nothing else to bond for those, which leaves 2 lone pairs left over. Okay, so now we have 2 big areas up here that are going to be like pushing the others away from it. So if we look at this and we are trying to find out how many electron groups there are, okay, so if I come down here in electron groups, I'm going to say 1, 2, 3, 4, 5, because each lone pair also counts as an electron group. So I have 5 electron groups coming off of that central atom. I have 3 bonded pairs. Okay, so there's 3 bonds coming off of this. And then I have 2 lone pairs that are not bonded to anything. So if I was just coming in here and I had that information and I was reading this chart, I would come to 5 for 5 total electron bonds. I have 3 bonded pairs, 2 lone pairs, which makes this shape T-shaped. Okay, so that's just going to give you an angle of right about 90 degrees. It kind of depends on what's bonding, but right about 90 degrees. And then you have your ball and stick model and then your Lewis structure. So that's how these work. We can go ahead and do a couple of examples though. So let me go back to this one. Okay, so I should be on this tab hopefully. So I'm going to go ahead and, oops, I can't turn that on, can I? Okay, so let's see if I can't get a pen up here. I have to close this and turn this back on. Here we go. All right, so let's do blue so we can see it better. All right, so let's pick one that's going to be a little bit bigger. So if I did, let's do phosphorus. So if I did phosphorus, like 1 phosphorus and 3 bromines. Okay, so let's say that this is the formula that I'm given. So the one that's by itself, like there's only one of them, is phosphorus. So phosphorus is going to go in the center. We're going to figure out how many valence shell electrons it has. So if I look on my periodic table, I know that it's in group 15, which means it has 5 valence shell electrons. So I'm going to put these on here, spread them out. And then the bromines, we look on the periodic table, we know that they all have 7 valence shell electrons. So we're again gonna put these on and kind of spread these around so that they're equidistant from each other. Probably should have done this in a different color. Sorry if that's all blending together. Okay, so each bromine has 7. It needs 1 more to be satisfied. So it's going to bond with one of the electrons on this phosphorus. Same thing down here. So this one needs 1. We're going to bond to that phosphorus. Same thing here. Hopefully yours is a little neater than mine. So what we have here is we have 1 lone pair left over. And sometimes it helps to like draw this out so you can visualize it a little bit better. So if I have my 3 bromines and my 1 lone pair. So if I'm looking at electron bonds, I have 1, 2, 3, 4. Okay, and then if I'm looking at bonded pairs, I have 1, 2, 3, and I have lone pairs, I have 1. So if you're looking on that chart, you're going to have 4, 3, 1. So if I flip back over to that chart, okay, so we had 4, 3, 1 on that. So you would come up here and figure out where the 4s are, find the 4s, and then the next one, your bonding groups, we had 3, and then we had 1 lone pair, so that's 1, so 4, 3, 1. Slide on over to this column, it's trigonal pyramidal. Okay, so it's going to tell you that your bond angles are going to be 109.5 degrees. This is what the shape would look like. Okay, so for on this, because we had that lone pair at the top, you're going to have some repulsion there that's pushing these down. So hopefully this has been helpful. This sheet is on Canvas. Let's see if I can't show you how to get there. Let's get here. Okay, so if I get on Canvas, just record my face, that's fine. So yours looks slightly different than mine. So if I go to student view, here we go. So we're in unit 4 right now. So unit 4 is going to pop up first, but if you slide down to unit 3, for these extra resources, there's a couple of things here. So oh, I guess I didn't stick it in there. I will. I'll put it in there for you. So I'll put that slide like in here by itself, so you can just click on it and open it up and not have to find it. It's on whatever day we did that, probably on day 3, maybe day 4. But I'll put it down here under extra resources so it's easy to get to. So I'll plop it down in here. But there's also this VSEPR model and molecular geometry resource. It's a little bit long, but if you, let's get in here. Oh, it wants me to sign in, and I'm not actually signed in because I'm not a student. I can't move my face. There we go. Let me show you. This has got kind of messed up here at the end. So if I authorize this, okay. This is from an online chemistry textbook. It's called LibreText. And if you ever need more help you can go to this website here, and there's tons and tons and tons of topics. So here, this just goes through and like gives you more examples. It goes into great detail. So if that's helpful for you, then I would suggest reading it. But if you think that adding more detail to it's going to be more confusing, then you can just skip it. But it does go through and it gives you examples of like every single type of bond and like what that would look like if I was like here with your lone pair cloud. Again, it was a good representation of that. So lots and lots of examples on that. Okay, so hopefully that's helpful. If it's not, please let me know and I will do another one, or if that's not the right topic that you needed help on, I'll figure something else out. But if this doesn't help you get through it, we might need to Zoom so I can just like answer questions as you have them. Or we can call, I can call you on the phone, or you can come in or whatever. So it doesn't matter to me. This week, my schedule is pretty tight as far as like before and after school, but I could Zoom like Wednesday. I have meetings tomorrow afternoon during my plan. I could Zoom Wednesday or Thursday. I could do after school Thursday or Friday. So that's up to you. Let me know if this helps or not, and I will talk to you later.